Good evening, colleagues. This is my presentation for aggregation function for data analysis in R. To begin with, I'll discuss the description of the data. The modified data consists of 671 samples for the energy use of the appliances. It has 5 variables, V1, V2, V3, V4, and V5, and one dependent variable V6. And V1 is the temperature in the kitchen. V2 is humidity in kitchen area. V3 is temperature outside kitchen area. V4 is humidity outside given as percentage. V5 is visibility from weather station, and V6 is appliances energy use in watts per hour. For the rest of the exercise, we have taken a sample of 340 data points from this data set. Correlation between the variables. The definition is correlation is a statistical measure that quantifies the degree to which two variables are related. Scatter plots are used for visualization. Scatter plots are useful when a data has multiple variables. Each row shows the relationship for a particular variable and other variables present in the data set. And if points lie around a line, then we may interpret that there is a correlation, that a correlation exists between the two variables. Whereas if the points are scattered, it indicates that there is no correlation between the variables. It is evident from our scatter plot that the variable temperature inside kitchen, that is V1, and temperature outside kitchen, which is V3, have a positive correlation with the dependent variable V6. The humidity both inside and outside, that is V2 and V4, and visibility V5, on the other hand, seem to have no correlation with the dependent variable, and also V2 and V3. On the other hand, V3 and V4 seem to have mutual mild correlation, which can be seen in the scatter plot. It is evident that the temperature inside and outside the kitchen area should contribute to more towards the causal root of energy appliance. A histogram is also used to represent the distribution of data. It shows the frequency of the data within a specified interval, and it is useful to understand the variability of the data. If you go to the next slide, and these are the histograms which is obtained from the data given. The first two variables are almost symmetric, that is V1 and V2. And the third, fourth, and fifth variables, which is V3, V4, and V5, they are slightly skewed to the, I can say the third, fourth, and the fifth variables are negatively skewed. And whereas the dependent variable is highly positively skewed, which is V6. Based on these distributions, we confirm that our transformation for each variable, we can confirm our transformation for each variable in the later exercise. Transformation of the variables, or all the transformed variables now are from 0 to 1 after scaling of the transformation, and as expected, the distribution of the selected feature variables remain unchanged as we have done in the scaling. The distribution of the dependent variable has changed from highly positive skewed to almost symmetric as expected. Next, we'll perform the model fitting with this transformed data. As you can see, these are the statistics of fitted models, error and correlation coefficients, where you have a weighted average mean, where P is equal to 1, then weighted power mean, which is P is equal to 0.5, and the other fitted models. The statistics of the fitted models, where we have a weighted average mean, P is equal to 1, and then weighted power mean, P is equal to 0.5, then P is equal to 2, and the last one. The importance of variables. As expected from our institution and analysis, the fitted models also show the same results, considering the best model. The temperature outside seemed to be the most important variable for making predictions, followed by humidity outside and then temperature inside for the first two models. For the third model, it seems to be the best one, and then the temperature outside seems to be the most important variable for making predictions, followed by temperature inside and then humidity outside. For the fourth variable, humidity inside seems to be the most important variable for making predictions, as you can see in this one. Overall, we see that the weighted power mean where P is equal to 2 has the best fitting performance. We accept this model as the best one as there is less complexity. Other two models have three variables and they have selected all four variables. All the models seem to have average error between 11 to 12% with weighted power mean where P is equal to 2 having the lowest among others. Hence, the weighted power mean has the best performance. Since we have selected the best model or the most suitable one, we can use the parameters we identified in order to predict the output of an unknown instance. The raw input vector given here are these, which after applying our transformation, we achieve the new values. And it results in this vector 0.7, 0.32, 0.53, and 0.68. Entering this vector for the best model into R produces the output of 0.6058, but this needs to have a final transformation as well. Hence, after applying the appropriate transformation, we undo the transformation applied to original one and we get the predicted value of 86.06, which is pretty close to the observed value of 100. Since we have fitted our models to a training data of 340, we would expect the model to perform well given the assumptions of the model. The features shouldn't be correlated among themselves, and the inputs taken are expected to have a relationship in general, and perfect fitting is expected. Some of the limitations of the model were sensitivity to the parameters. The choice of the power parameter and weights can significantly impact results. Selecting the appropriate values for these parameters may require domain knowledge or sensitivity analysis. Linearity assumption, weighted power mean aggregating functions assume a certain level of linearity in the aggregation process. This may not capture complex or non-linear relationships. Another limitation of the model is data distribution. This one, where the performance of the weighted power mean functions can vary depending on the distribution of the data. In cases where the data distribution is skewed or multimodal, alternative aggregation models may be more appropriate. And the next limitation is interpretability. Interpreting the meaning of power parameter is in practical terms can be challenging. And data consistency means that's another limitation of the model. The effectiveness of weighted power mean aggregating functions depends on the consistency and reliability of the data. And the last one, loss of information. Aggregating data using any method, including weighted power mean functions, involves some loss of information. The aggregated value is a summary statistic, and some details of the individual data points may be lost. Thank you.